Welcome back to the Explainer, where we decode the hidden rules shaping our world. Have you ever looked up at a massive concrete ceiling or maybe walked across a sprawling bridge and just wondered, how on earth is this actually holding up? Well, today we're going to unlock the fascinating hidden physics of the built environment. We are looking directly at the invisible forces that literally keep everything from crashing down around us. So here's the pretty high stakes question. How do engineers guarantee the floor beneath you won't simply collapse under the weight of your furniture, people, and its own materials? It's not magic, right? And it's definitely not guesswork. The answer lies in a universal language of forces, stress, and limits. And today, we're going to learn exactly how to read it. Now, take a look at this. Yeah, I know, it kind of looks like an intimidating wall of math and Russian text, but this is actually a structural engineering cheat sheet. It's this elegant, highly organized matrix of how beams behave under intense stress. Now, stick with me here. I promise that by the end of this explainer, you're going to be able to read this document like an absolute pro. Okay, let's dive right into this. Here is our roadmap for unpacking this whole thing. We'll start with the secret language of beams, decode the columns, look at the fixed pinned family, then the fixed family, and finally, we'll wrap it all up with the architecture of safety. Part 1. The secret language of beams, predicting stress. To really get this document, we have to look at the fundamental problem it's solving. Every single day, gravity is constantly threatening to snap the materials that make up our buildings. So engineers need a bulletproof way to predict exactly how those materials will bend. This single page is the ultimate toolkit for that exact problem, laying out 8 distinct survival scenarios. Each row you see represents a totally different way a horizontal beam handles weight and stress. Moving on to part 2, decoding the columns, reading the matrix. Let's conceptually translate these Russian headers into something a bit more anatomical, just to make all this dense technical jargon feel a lot more intuitive. Column 1 is the beam scheme. Think of this as the skeleton. It shows exactly how the beam is anchored and where the outside weight is pushing down. Column 2 holds the bending moment diagrams. You can think of this as a map of the muscle stress. It visually highlights exactly where the beam is feeling the most internal strain. And column 3? Those are the formulas, the genetic code, if you will, that calculates the exact numerical limits of the beam right before it fails. Now, if we look really closely at our skeleton column, you're going to notice 2 main types of attacks on our beam. First up, we have point loads. These are labeled with a P or F and a single heavy arrow. Imagine a massive heavy pillar resting on exactly one specific spot on a floor. Then we have distributed loads. These are labeled Q with a whole row of smaller arrows. This represents weight that's spread evenly across the entire surface, sort of like a thick, heavy layer of snow sitting on a flat roof. And this brilliantly illustrates how the specific type of load dictates the ultimate shape of the stress inside the beam itself. If you guide your eyes over to the shaded shapes in the middle column, our muscle stress, you'll spot a very clear visual pattern. Point loads create these sharp, jagged, triangular stress shapes. The stress peaks exactly where that single arrow pushes down. But distributed loads, they create these beautiful, sweeping, parabolic curves because the stress builds up gradually toward the center of all that spread out weight. All right, part 3, the fixed pinned family. This covers rows 1 through 4. Looking at the top half of our decoder ring, in rows 1 through 4, we see a distinct visual shorthand in the diagrams. At point A, over on the left side of the beam, there's a vertical line with little diagonal hashes. That means the beam is firmly fixed, essentially buried deep into a concrete wall. It cannot move or rotate at all. But at point B on the right, you'll see a little circle or a triangle resting on a surface. That is a pinned or rolling support. It holds the beam up vertically, for sure, but it allows it to flex, hinge, or slide just a tiny bit horizontally as weight is applied. Take a really close look at row 2 here. We have that uniformly distributed load pushing down across our fixed pinned setup. Notice that middle column. Again, because the left side is trapped perfectly in the wall, it fights back hard, creating a harsh spike of stress right at the anchor point. But as your eyes move to the right, where the beam is actually allowed to roll or hinge, the stress naturally creates that sweeping parabolic dip. The beam bends, sure, but it bends in a highly predictable way. Part 4, the fixed family. That's rows 5 through 8. Let's see how this changes the game. In this family, step 1 is to heavily fix the beam into a wall at point A, but now step 2 is to heavily fix it at point B as well. Both sides have those hashed lines now. The result is an incredibly rigid structure. Because the beam is trapped completely firmly at both ends, it can't rotate or roll at all. So, it has to absorb the weight entirely differently. Just look at row 5 for a second. We've got a single point load right in the middle of a fixed beam. Because neither end can move even a fraction of an inch, the beam forcefully distributes the stress back toward both walls. In the center diagram, you no longer see just one simple triangle. Instead, it's this complex double triangle geometry. The stress dips in the middle under the weight, but violently spikes upward at both walls where the beam is basically desperately trying to rip itself out of the anchors. And finally, part 5, the architecture of safety. Let's talk about that formula column. Okay, please don't let the dense algebra scare you off here. These formulas are really just a recipe. They are combining a few very specific, measurable variables to find a beam's exact breaking limit. L is simply the length of the beam. P and Q are those loads we talked about earlier, how much weight is actively pushing down. M is the bending moment, representing the twisting force. And variables like E and I simply represent the stiffness of whatever material you happen to be using, like steel versus wood. Like I said, it's just a recipe for structural integrity. So the absolutely crucial point to take away is this. Look at how the variable L, for length, is literally everywhere on the right side of the page. It's squared, it's cubed, it's divided. It proves mathematically that a longer beam is exponentially more vulnerable to bending than a shorter one. This sheet demonstrates that certain structural truths are absolute and universal across all building designs, no matter what you're building. It's just wild to think about how much invisible chaos is being perfectly managed right above our heads every single day. Next time you walk into a large room, just look up at the ceiling and ask yourself, what invisible forces are those beams calculating right now? Are they fixed pinned? Are they fixed? Are they fighting off a point load or a distributed load? Every structure tells a pretty incredible story of physics, and now you hold the decoder ring. Thanks for joining me on The Explainer. Keep learning and stay curious.